Areas of rectangles and parallelograms. Let's dive right in. I got this rectangle. It is a 3 by 5 rectangle, and if we want to find the area of this, we need to recall that area is the measurement of the space inside of a polygon. It's a two-dimensional measurement. So if this length down here is 5 units, what's really going on here is I can draw in these lines. I have them pre-marked, so this will be pretty close to accurate, although it won't be perfect because I'm trying to move quickly. And then I have some marks on the side over here. And what will happen this side is length 3, so it's 3 boxes tall. This bottom part here is length 5, so it's 1, 2, 3, 4, 5 boxes tall. And you'll notice if we were to count all these boxes, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. We have 15 boxes of the exact same length. Notice that these boxes are all perfect squares. We don't know exactly the measurement of this particular one. It's 15 square units. Generally, we'd work in inches or miles or meters or whatever the case may be. This is just an arbitrary length here. So we would say that the area of this rectangle is 15 square units. And I'm sure you've seen this formula before, but here's why it takes place. So the area of a rectangle, specific for rectangles right now, is we'll call it length times width. This distance here will be our length, the longer one, and the width will be the other distance there. So if we're to abbreviate this, we'd say area is length times width, which in our case is 5 times 3. 5 times 3, of course, is 15. So again, I'm not kidding myself. I'm sure you've seen this formula before. I get that. Here's why it's true, though. This is the why behind it. Ancient Greek mathematicians, they didn't do so much with algebra and numbers. They were more interested in shapes and stuff. So if they were to multiply, two lengths together, they would envision this rectangle. For us, we do 3 times 5 all day. Maybe you're at the store and there's something for $5 and you want to buy 3 of them or whatever. But for them, it was all geometrical. So here's the why behind it. And then, of course, over the last few thousand years, we've simplified it quite a bit, and this is what you've seen before. Okay, let's talk parallelograms. Same story. This one I went ahead and I marked in all their boxes. This one has a base length of 4, and from the floor to the ceiling, as it were, as it's situated right now, is exactly 3 units. So how would we find the area of this thing? Well, what I want you to notice is that this is essentially a square with some triangle, or a rectangle anyway, with triangles attached to both sides. So if I were to take this whole section, all this stuff I've shaded in red, and I were to just move it, rotate it, and slide it over here, what would happen is I would just be continuing out this rectangle. And I would have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 units. Of the same sort of situation if we can visualize that we're taking one of the chunks off one side and moving it to the other. This works with parallelograms because parallelograms, opposite sides must be parallel and parallel and congruent to one another. Same is true for the other pair of opposite sides. So the area here is, we call it base times height. Here is the height. Area is base times height. So for us, that is 4 times 3, which is 12 square units. And of course, we counted our 12 squares in here. So this is how you find the area of a parallelogram. Do you have to show all of the boxes and stuff? No, you don't. But I need you to be thinking in the back of your mind, like, oh yeah, that's where this stuff comes from. So here, if you were just to see this thing out in the wild, like, oh, base of 4, oh, the height is 3, cool. Then I just multiply 3 times 4, and know that what that means is the area inside of the figure has exactly 12 of these boxes of the same exact measure here. Okay, This shape is kind of wonky. This is called a composite figure where we have multiple shapes kind of connected together, and we're going to find the area of the whole piece. So notice for this one, there's multiple ways to break it down. Would be to separate it into a rectangle, the one on top, and the parallelogram, the one on the bottom. So the gist of this thing is we're going to find the area of the separate chunks, add them together, that's the area of the whole shebang. So on top here, I'm noticing that this is length 4 and a height of 1.5 or a width of 1.5. So this area of just the top portion, the rectangle, is 4 times 1.5. 4 times 1.5, well, half of 4 is 6. So sorry, that's not true. Half of 4 is 2. 2 plus 4, that's what is 6. So it's 6 square units for the top. Now for the bottom, we got to do a little bit of calculating. We know the base is 4, so the area is 4 times something, which that something is whatever this height is. We got to figure that out. Well, I know the whole, from top to bottom, the entire figure is 3.5. And I know that this rectangle has a height of 1.5 over here. So we can even insert that and say that this is 1.5. So if this chunk is 1.5, the whole thing is 3.5. The remainder here, when you do the subtraction or the difference, is 2. So this bottom section has a height of 2. Therefore, the area of that parallelogram is 8 units. So the area of the entire thing then would be 6 plus 8 for 14 units squared. All right, here's the how and the why of finding areas of rectangles, of parallelograms, and composite figures. You'll be using these formulas: areas length times width for rectangles, areas base times height for parallelograms. Notice they're basically the same thing, because when you take this triangle and you move it, it's just a rectangle. So it's the same sort of operation here. And then, of course, we can attach them and find areas of bigger figures. These figures will grow. They'll include triangles. They'll include circles. They'll include other things. So be aware of that. But for today, we're just learning the idea of composite figures with rectangles and parallelograms. All right, let's dive into some practice problems. You got this.